So we said that acids and bases are classified based on their strengths, which we can now say is the amount of H3O plus and OH minus produced per mole when a substance is dissolved in a solution. We can then use this understanding to classify acids and bases based on their strengths. And the first group are the strong acids, okay, folks? That's what we're going to start with first. And an example of a strong acid is HNO3 Thor, where it's going to dissociate into H plus or H3O plus ions and the nitrate anion. And of course, we're here to learn why, but we first must layer another concept, and it's an oldie from Chem 101, and that is electrolytes. Okay, folks? Electrolytes are basically ions with an electric current that have the ability to conduct electricity when it's dissolved in water. And so what happens is you're going to have substances like HNO3 that's going to dissolve in water, and you can see it here, for example, you have HNO3 mixed with water, and they're going to dissociate into these ions, and these ions have the ability to conduct electricity. And so therefore, acids and bases are electrolytes, folks. And so their strengths are going to correlate with electrolyte strength. And there's two types of electrolyte strengths that we look at. We look at strong electrolytes and we look at weak electrolytes. Strong electrolytes are going to dissociate completely in solution into its ions. So for HNO3 Thor, which represents a strong acid, it's going to dissociate specifically into H3O plus or H plus as we see, and NO3 minus or the nitrate anion here. And as you can see, there's an arrow that only points in the forward direction. So we talk about equilibrium, but for strong acids, and we'll see this for strong bases as well, we do not actually have to use the overall equilibrium value or expression because we already know it's going to just strictly go into the forward direction, making it easier for us to specifically get this concentration here on our own through calculations like with pH and everything like we saw before. Okay, folks? So a lot of times when you have strong acids or strong bases, you're going to see that there's one arrow. This does not mean that we are not in equilibrium. This just means it's an easier way for us to be able to distinguish between strong acids and weak acids, and an easier way for us to be able to understand that these strong electrolytes are going to disassociate completely. Now, of course, outside of a strong electrolyte, you're going to have a weak electrolyte. What do? They're going to disassociate slightly. That means we're going to have, yes, the ability to form these ions in the forward direction, but those ions are also going to go back to form the reactants in the reverse direction. Okay, folks? That means when we have weak acids and weak bases, guess what? We are dealing with equilibrium problems. So it's a little bit easier to distinguish here. Strong acids and strong bases, a lot of times you will not have to have an equilibrium problem because we're just going to be going in one direction, the forward direction. But with weak acids and weak bases, we'll see we do have specific equilibrium constants that are related to an acid dissociating or a weak acid dissociating and a weak base dissociating. Okay, folks? One way to show generically a strong acid, which would be HA, because remember, we're still dealing with the Bronsted-Lowry definition, so it has to donate a proton. So we have HA here, plus mixing it with water, and this proton is going to be going over here. It's going to form H3O plus, and you're going to be left with the conjugate base, which is A minus. How do I know it's a conjugate base? Because we already talked about conjugate acid-base pairs. We know that HA and A minus are a conjugate acid-base pair, just like H2O and H3O plus. So whether we're talking about a generic strong acid or HNO3 Thor here, no matter what, it's going to be in one direction, in the forward direction, and you're going to form the conjugate base and, of course, H3O plus here. Let's go ahead and see that visually. In the bar graphs here, we're going to have before dissociation, so before HA has donated its proton, and then we're going to have after dissociation. After this has been mixed with water, what is left over? So as you can see here, the H3O plus concentration, the A minus concentration are the only bars that are left over. There's nothing left in the HA concentration. But before, we had all HA. This is telling me that since all the HA is going to be used up, the H3O plus concentration is equal to the conjugate base concentration, which is going to equal to the initial amount of HA that we started with. And so that means our HA is completely used up, and there's virtually no HA molecules that are present. And in lab, the one way we do to be able to prove this is that we take a dilute amount of a strong acid, we mix it with water, and then we basically take a picture of it. And we see that we have, of course, all the products left over, and we have no HA left. That's the reason why we keep this arrow strictly in the forward direction, because again, they're all equal to the initial amount of HA that we started with. A simpler way to think of it would just be to say that we can have no HA. Let me write this here. I'm getting better as well. We have no HA molecules at equilibrium. So there's no HA molecules at equilibrium here. And also that means that the amount initially that we have of HA is going to be equal to whatever we have left over for H3O plus and the conjugate base. Also, we can go further and get the Q value, which we know is going to simply be the K value here. And since we don't have any HA left over and H2O was 1, when we go ahead and take our overall reaction here and get our Q value, we're only left with H3O plus and A minus concentrations. And since we have a lot more of the product, our QC, which is equal to our equilibrium amount, is going to be greater than 1. If it's greater than 1, that means we have way more products, right? Which makes sense because our acid is very, very strong. It's going to disassociate completely. So we should only have products left over. And that's just one way to kind of verify that we're dealing with a strong acid as well. And so because the reaction with strong acid is essentially complete, we usually don't express it as an equilibrium process, okay, folks? Because there's no undisassociated HA left over. All this is gone. And so again, it's easy for me in my head, if I have to distinguish between strong acids and strong bases and weak acids and weak bases without even knowing any of them, I would distinguish them first by the arrows. Knowing that strong acids and strong bases dissociate completely, I will look at the arrows, really start trying to look at the reactions given. All the reactions given here, we know they're going in one direction. That to me in my brain is going to start signifying, okay, this must be a strong acid. This must be a strong base because it's completely disassociated. All right, folks? So we're all about layering information. So if we're looking at HNO3 Thor, what else can we say about him? Now we can say HNO3 Thor is a strong acid. He's also an Arrhenius acid, and he's a Bronsted-Lowry acid. All of that just by being able to, again, layer information from the previous portions of this lecture. Okay, so therefore, folks, strong acids equal strong electrolyte. We'll see the same thing. Strong bases equal strong electrolyte. Let's focus on strong acids first. There are two types. There's hydrohalic acid, and then there's oxo acid. So let's go ahead and break this down. Hydrohalic. Hydro, that means it's going to have H, and then it's going to have a halogen attached to it. Not every halogen, some halogens. And then we have the oxo acid. That means, yes, you're going to have your H involved, your protons, your ionizable protons, but you have to have some number of oxygen atoms as well, okay? And that number of oxygen atoms is going to tell you that you're dealing with an oxo acid. There's two types of these strong acids that you want to memorize. Of course, there's plenty to know, but there's 6 that we have here that are the most common. As you can see, HNO3 Thor is right within the strong acids group. Let's get some more details of these two types. So for our hydrohalic acids or our hydrohalic strong acids, we're going to have hydrogen and a halogen. So the 3 halogens that we're focused on is going to be chlorine, bromine, and iodine. Okay, folks, as we get further and further, some people may be saying, but why aren't we going to use the other halogen? We'll get more details of that. But right now, that means any other halogen you get in this course is what type of acid? A weak acid. If it's not one of these hydrohalic acids, then the other halogens are considered a weak acid, and that's one way that I always distinguish things. I'll tell you straight up what I do. I only memorize the strong acids and bases. If I was a student, I'll memorize, of course, some of my weak acids and bases that I see commonly, but I would only memorize my strong acids and bases. That way, they're in my head, they're drilled in my head, and if I see anything outside of what these strong acids and bases that I'm going to give you here, then I automatically know they're weak acids or bases. And it's going to make it a heck of a lot easier as you're going through the exam and stuff as well. Okay, folks? So these are our 3 hydrohalic acids. And then we have 3 oxo acids. So an oxo acid means that you have the number of oxygen atoms that are attached, whether to a polyatomic ion within this overall acid here, has to exceed, and remember exceed, the number of hydrogen atoms by 2 or more. So for HNO3 Thor, we have 3 oxygen atoms. We have 3 oxygen atoms minus 1 hydrogen atom, and that equals 2. So have we exceeded by 2 or more? Yes, we hit the quota by looking at 2. Let's look at H2SO4. We have 4 oxygen atoms minus 2 hydrogen atoms. We are at 2. Remember, we have to be at 2 or more to fit the oxo acid standard to be a strong acid, okay, folks? And of course, all the other definitions that we're layering on. 3 examples that we have here is HNO3, H2SO4, and HClO4, which is simply going to be perchloric acid, sulfuric acid, and nitric acid. Hydroidoic acid, hydrobromic acid, and hydrochloric acid, okay? So these are the 6 that we usually have. Now, when you're stopping here, you want to think, HNO Thor, we know he's a strong acid, Instead of just saying strong acid now, we can say HNO4 is a strong oxo acid. He's also an Arrhenius acid and a Bronston-Lowry acid. Again, layer on the information. And don't forget those flashcard moments, folks. So for example, if you don't want to use a flashcard moment for this and you want to go ahead and just memorize the six acids that you see here, that's fine. But you also can use a mnemonic to help you remember these 6 acids. So it's really up to you and how you want to basically recall this information. Okay, folks? So let's just get an example mnemonic here. So here's an example mnemonic. HNO3 Thor crushes in battle, protecting society. So HNO3 is going to represent nitric acid, HNO3. That makes it easier, right? HNO3 Thor is going to be Thor. You can just say HNO3 crushes in battle, but it's better if you just say HNO3 Thor. It makes more sense. And then crushes, we have C. C is going to represent fluorine. So we can say hydrochloric acid. So HNO3, nitric acid, hydrochloric acid for crushes in battle. So it's going to be IN. That's going to represent hydroidoic acid or HI, right? Battle is going to represent hydrobromic acid. Protecting is going to represent perchloric acid. And society is going to represent S, which is sulfuric acid. So if you want to use this mnemonic, you can. Of course, it's going to be how you organize your flashcard moments to get you through. Now let's get into a couple of examples. If we know these are our 6 strong acids and we're trying to come up with ways to remember them, right? Some folks will just remember these 6 and just remember the 2 types. Some folks will use them a mnemonic. Some folks will just use note cards and recall. It's up to you. Let's go ahead and get an example to ask one question. Is this a strong acid or not? Now, of course, you have the list here, but we still want to ask questions. So let's go ahead and do that. Okay, is it a strong acid? The first one up is HF. Without having any other information, except what we have on this screen here, is HF a strong acid? Automatically, the answer is going to be no. So if it's not a strong acid, what type of acid is it? It's a weak acid, folks. How do I know that? I only have chlorine, bromine, and iodine that I know in my head is going to be the strong acids that are common to us. So if I have fluorine, which yes, it's another halogen, but it's not a part of the group, I know it's automatically a weak acid. What about H2O? Is it a strong acid? Well, when I look at H2O, I see that we have oxygen. So I know I'm looking at the oxo acids here, okay? And so the idea is that you have to have at least 2 or more oxygen atoms that exceed the ionizable protein. Not proteins, protons, folks. So we have oxygen, there's only 1, minus 2 hydrogens. This is equal to -1. So water is definitely not a strong acid. It will be considered a weak acid. And it's also considered a weak base. Okay, folks? Now let's look at CH3COOH or acetic acid. Again, I see oxygen, I'm thinking oxo acid. I have 2 oxygens here, minus, it looks like there's going to be 1 ionizable proton, so that kind of works out. This is a methyl group, so I'm looking at this, it's probably going to be my proton that's donated. So it's -1. Okay, that works. Well, is it a strong acid? I'm here to tell you, folks, absolutely not. And we're going to get details on this. But the reason why this is not a strong acid is not because it doesn't fit the oxo acid portion. It's because when we take this CH3 and mix it in with water, it does not disassociate completely. So we get down to these 2 types and it's all about memorizing, but I want to throw this in here so that we never forget the overall definition of a strong acid, and that it's also a strong electrolyte, which has the ability to disassociate completely, okay? Therefore, when it disassociates, we shouldn't see any of this acid portion left over. We should only see H plus or H3O plus and the conjugate base. But guess what? This fits the bill as far as being an oxo acid, but when we mix this CH3COOH minus in water, it does not disassociate completely. It actually is going to be an equilibrium, and therefore it is a weak acid. Now, let's go ahead and move on to strong bases, folks. So like strong acids, strong bases also dissociate completely into ions in water, and of course are thus classified as what? Good old strong electrolytes. That means we also do not express strong bases in solution as an equilibrium process, and so we will see that 1 single arrow just like we have here. Now, one example that we see of a strong base would be like NaOH Black Panther. Now, we know that Black Panther is going to represent NaOH Black Panther and dissociate into Na plus and OH minus ions, which cause basicity, right? We also know that NaOH Black Panther is a Bronston-Lowry base. And now we can say that NaOH Black Panther is going to be a strong base because when it does disassociate into Na plus and OH minus, it doesn't go back and create NaOH. It completely just disassociates into these 2 ions as products. And those ions have the ability to be strong electrolytes. Okay, folks? And normally what we see when we're talking about water-soluble compounds that are strong bases, they usually are going to contain two types of ions. We know OH minus, so that's one we can think of, but also O2 minus. When you see O2 minus or OH minus that is being formed in solution, usually dealing with a strong base. And usually it's the cations that are attached to OH minus or O2 minus that allow us to classify strong bases themselves. And we usually classify strong bases based on groups on the periodic table. So we're going to have group 1 and our group 2. So we have our group 1 or alkali metals, and then we have our group 2 or heavy alkaline earth metals here. And they represent our cations that are going to be attached to our anion of OH minus here or our anion of O2 minus here. So with group 1, we know they're going to give up one particular electron, right? And so our lithium, sodium, potassium, rubidium, and cesium are all going to give up one single electron. And so that means when they create a compound with OH minus, they're simply going to just be the metal and then OH. And so we see a generic formula here of MOH. If these individual lithium, sodium, potassium, rubidium, and cesium are attached to O2 minus, you'll see the generic formula of M2O. So it'll be Li2O. It'll be K2O, it'll be Rb2O, right? Again, you're using the anions that are given to you. The other type of cations are going to come from group 2, and it's only these three here, and that's going to be calcium, strontium, and barium. And so the M for these generic formulas are going to include these particular metals here. And so you can have CaO here, and that will be a strong base. Why? Because these are all group 2, and so they're going to have the ability to be 2+. Just like these are 1+, they're going to give up 2 electrons. And so O2 minus needs to gain 2 electrons, and one of these metals needs to give up 2 electrons. And so when they create a formula here, it'll just be simply CaO. You also will just have SRO here and BaO. And then, of course, if you have your calcium attached to your hydroxide, then we know it's going to be, say, for example, Ca and then OH2, just to use this formula here. That means we have our calcium, which is the 2+ charge, and we're going to need 2 OH minus charges in order to balance it. So that's why we have OH2 here. And so that's just little ways to actually start classifying those strong bases. Again, what I do is try to memorize what's given to me, group 1, and then the handful of group 2 ones, memorize what's given to me. Anything outside of this and anything outside of these parameters would be considered a weak base, folks, right? So we got to kind of keep that in mind when we're layering information and distinguishing. So if I'm thinking at or looking at NaOH Black Panther, I can say that NaOH Black Panther is a strong group 1 Bronsted-Lowry base. And of course, I also can use a mnemonic to help me memorize these group 1 and group 2 strong bases. And that's just one way to do it as well. And I'll just give you an example here. Carefully, Black Panther strikes. Nox Loki rescues civilians nightly. Okay, so the Ca from carefully is going to represent calcium. The B is going to be barium, the S is going to be strontium, the K is going to be for potassium, the L is going to be for lithium, the R is for rubidium, the other C is going to be for cesium, and then finally the N is for sodium. So that's just one little mnemonic that you can use. Or you can simply memorize the bases that you see here. Again, a little trick that I always use is to memorize the strong acids and the bases the best way I possibly can. Anything outside of that would be considered weak, and that'll be an easier way to distinguish. Also, to remember these details and definitions that we have for strong acids and bases. Now, again, we want to play the same little example game that we did for strong acids, and that is this a strong base? So let me get some examples ready, and then we'll be able to see those. So what do we know about strong bases? First, we know they must completely dissociate in water. We won't know the details from this. I'll be telling you that, right? And we know they must contain the OH minus anion and the O2 minus anion. And we have different cations that represent strong bases that we memorize. So first we have H2O. Now again, this does include the OH minus anion, so that is something that's true, right? We also know that water is auto-ionizable, right? So it's in equilibrium. So that's definitely not going to be something that just completely, water is not going to be a molecule that completely just creates H plus and OH minus and that's it. Then we have HS minus. So as you can see, we have an S. Well, make sure that's an S minus here, folks. Okay, so you have HS minus. Again, it does not contain O2 minus or OH minus, so that's easy to get rid of. Also, we look at a strong base here, NH3. Okay, folks. Now we know that NH3 is a base because it has the ability to accept the proton. We saw that with NH3 Iron Man. But is it a strong base? The answer is no. It does not contain OH minus or O2 minus, okay? It does not contain any of the cations, and so definitely it is not a strong base. It will be considered a weak base, just like everything else I'm showing you here. Now let's look at NH4OH. Yes, it can dissociate into OH minus. I see some OH minus that can come from here, right? But guess what? It's also not going to dissociate completely. It will be in equilibrium. So even though it has the OH minus there, it is not a strong base. Finally, let's look at HCOO minus. Do we see O2 minus here? Do we see OH? We don't see OH, right? Now, again, you might be saying, wait a minute, there's this carbon here is attached to, it's double bonded to this oxygen, it's single bonded to this oxygen here. Okay, and this oxygen has a minus charge, so there's no O2 minus that is going to be attached to one of these metals, so this would not work as well. That means anything outside of this is going to be considered a weak base. This HCOO minus is a weak base. NH4OH, NH3, HS minus, all of those will be considered a weak base. Remember, the goal here, folks, is to make sure that you remember those strong acids and those strong bases. These are the most common ones I can give you. I can add more or less, but I want to give you the most common ones that you're going to see for these, exams, and also when you go to organic chemistry, different labs, etc., etc. So take heed of my words. Make sure you're using those flashcard moments and stopping yourself and writing down information. And of course, go back and review this and review examples to make sure that you can layer information as well. Let's get into the next topic, folks.